Hello everyone. Today we are going to talk about a concept in calculus that is used frequently in dynamics, especially when we talk about a coordinates called path coordinate, or sometimes we call it normal tangential binormal coordinate. So first, let's look at this notion we call radius of curvature. And then we see how we are going to use it in dynamics. So if you have a circle, the definition of radius for the circle is clear, right? It's the constant distance from center to any point on the circumference. But if you have an arbitrary curve, so here y is a function of x, and this is an arbitrary path. Now, at any point, if you want, you can draw a circle tangent to the path, a local tangent circle. So let's say at that point, I can go ahead and draw a circle that is tangent to the path at that point, like that. Or if I go to this point, let's say, then again, I can draw a local tangent circle like that, probably a little bit smaller, and so on and so forth. And the location of this local tangent circle with respect to the path and the center of it and the radius of it does depend on the location along the path and the function itself. So, for example, here that if I consider this like the road and I'm driving along this road, or the particle is moving along this road, when you're turning but the turn is rather wide, the radius of this turn is larger than when you go through a sharper turn, correct? So for example here, that it is even smaller. If I want to look at the radius of curvature and the circle that is tangent, it is going to be even smaller because I'm doing a sharp turn. Okay, on the other hand, the more your path resembles a straight line, your circle, the tangent circle, gets what? Bigger and bigger. So here, if I want something, and this is almost close to, if you see almost close to a line, then the tangent circle here is going to be really big. And the reason for that is there is really no curvature. Okay, this is called the radius of curvature, radius of a tangent circle. And locally, you can say that a straight line is a circle, but the radius of that circle is what? Infinite. So now the question is this: how can I calculate this radius? So here, again, the radius of any of the circles, I show it with radius of curvature, and the parameter I use to represent it, I call it the rho, the Greek letter rho. And the question is, if I give you the criterion for the path, so here this is y as a function of x, and I give you this location, whatever you want, let's call it x star. Can you give me this rho, which is clearly a function of location, right? This rho of x. Can you give it to me? And yes, in calculus, you will see that if it's taught to you in calculus, that the rho as a function of x is equal to 1 plus y prime, right? Or dy over dx. The whole thing squared. And then this numerator is to the power 3 over 2 divided by magnitude of y double prime. And these functions of x can be evaluated at any point. So if I evaluate it at x star, it gives me this row. If I evaluate it at the next x, it gives me that row for that location, and so on and so forth. So now I want to first demonstrate this formula and how to use it through one or two examples, and then I'll show you where is it that in dynamics and in real life we use this notion of radius of curvature. So first thing I would like to do is to show the usage of it through something that is obvious. And of course, nothing is as obvious as a circle itself. So here, I assume that the path or the function that I am going to find a radius of curvature for it is a circle itself. Okay, so here this is y, this is x, this is a circle with radius of r, and the point at which I want to find the radius of curvature, I consider it here. So what's the radius of curvature there? Clearly, since it's a circle already, it should be equal to r. So ahead of time, I know what my answer should be, but let's show it. So to find that, first I need to know the criterion for my curve. What is this? So here I have two semicircles, and I'm going to only use the top portion of it. And clearly, as you know, the equation for a circle in general, if it's centered at origin, it is going to be x squared plus y squared equal r squared. And so from here, if you take x to the other side and take the square root, then y is going to be what? It is going to be plus or minus r squared minus x squared, the whole thing under square root. Now, as I said, if I only care about what? Because this point is on the top semicircle, and this is where, clearly, this point is where y is what? Positive. Therefore, out of these two, I only would choose what? The positive solution. So that's my function. The location of it is at which x? Clearly here, x is what? 0. So I'm going to evaluate that formula I just showed you for this function at x of 0. Let's see what we get. So that is my y. Now, clearly I need first and second derivative. So what is the first derivative? Dy over dx. So if you know, it is going to be negative 2x divided by 2 times the square root. And you can simplify the 2's, so you will get negative x over the square root. That is the first derivative, and then from here, if you want, you can take another derivative, and so you will find your second derivative to be, this is a rational function. You can keep the negative outside. It's going to be the derivative of numerator, which is 1 times the denominator minus the derivative of denominator, which, if you remember, that's the same as this guy here, times numerator, which is x. And this is divided by that square root to power 2. Correct? So these are all r squared minus x squared. And if I further simplify it, okay, these two are going to be x. And here, this one will be multiplied by that. So here you have x squared, r squared, negative x squared. If you simplify, you will get r squared divided by square root of this to the power 3 over 2. Okay? And, 5 over 2 actually in this case. Because that's to the power 2, and then this is another power, that's 3, so it's actually like this. If you brought it out of the square root, then it would be 3 over 2. So now let's calculate my radius of curvature. Radius of curvature is going to be 1 plus y prime squared, so you have to square that whole thing. Then raise the whole thing to 3 over 2. And then divided by magnitude of this one. And then evaluate this whole thing at which x? At x of 0. So all you need is to plug in x of 0. If you do, then this whole term is going to go away. This whole term is going to be r squared. Square root of that is r. So this whole thing is going to be r cubed. So the result is going to be 1 over r. Correct? When you simplify this whole denominator, it is going to be 1 over r. And so the result is going to be r, as expected. So you clearly see that this formula works just fine. And it gives me something that I expected. But if it's any other function, okay, it's not really any major deal. So for example, if the equation for the path is a parabola, so this is like y equal x squared, and let's say at point 1 you want to find out that what's the equation for what's the amount of radius of curvature, then all you need to do is to apply that formula. So here, let's say this is my tangent circle at that point, right? And then, of course, the value here, x of 1 is y of 1. And if you want rho here again, it's not a big deal to show that because y prime or dy over dx is 2x and y double prime is 2. So rho is going to be 1 plus 2x squared, the whole thing to the 3 over 2. Divided by absolute value of 2, and then this whole thing calculated at x of 1. And of course, this is going to be 2 squared 4, 5. So it's going to be 5 to the power 1.5 divided by 2. And I don't think that is a hard thing to calculate. So 5 to the power what? 1.5 and then divided by 2. And the answer is going to be 27, but you always need to make sure 5 to the 2.5 is 50, that 5, so divided by 2, that's right, 2795. Okay, and that's this r for this function. So this is the notion of radius of curvature. Now, where would you use it in real life? Well, one of the coordinates that we have to describe the motion of a particle or a rigid body in general is called path coordinate. I'm sure in your dynamics course you have learned about Cartesian or rectangular coordinate, or XYZ we call it, cylindrical coordinate, the 2D version of cylindrical, which we call polar coordinate, and spherical coordinates. But another way to describe the motion of a particle, as I said, is using a coordinate frame which we call path coordinate, or we call it tangential-normal-binormal. So here, this is a 2D version of it for now. If I have a path along which the particle is moving, and I know the equation for this path, so I know y as a function of x, I know that. And I also know how fast this object is moving along the path. So if at each point I draw a tangent to the path, and that is the speed v, I know this speed v, okay, as a function of time in general. So consider it like when you're driving along the road. So this is a car, you're driving along the road, and using your odometer, you can find your speed or record your speed as a function of time, and you know the criteria of the path you're moving along it, and you want to describe the position, the speed or velocity in general, and acceleration of this particle along the path. So how would you do it? So the way to describe it is, instead of fixed unit vectors I, j, and k, or x and y axis unit vectors, what I do, I attach a frame to the particle that moves with it, and the axes of this are, one of them tangent to the path at the point, the other one is normal to the path at the point. So basically, if I go here and I want to show you, one axis is going to be tangent to the path locally, and this unit vector in that direction, I call it E tangent. The other one is going to be perpendicular to this E tangent, and I call it what? E normal. Okay, and this guy moves with the particle along the path. Clearly, ET is the direction that the velocity is, and EN is in the direction that goes toward the center of curvature, right? Because if you know the notion of center of curvature, right? So if I draw this local circle at that point, of course it has to be a little bit smaller. But if I do it something like this, correct? And let me correct this EN for this new shape. Let me make it a little bit more accurate. So this is the center, and this is EN, right? And that is ET. Oh. So now, as you know, the normal to any circle at any point is always toward what? Toward the center, right? You know it from the definition of circle. That's the normal line at any point to the circle always passes through the center of the circle. That's the radial line at that point, because tangent is always perpendicular, correct? Tangent is always perpendicular to the circle at each point. So if I use these two, as I said, there is a third unit vector, but we'll talk about it later. If I just use ET and EN right now to describe the axes of this new coordinate frame, we call it tangential normal, then I can show that the velocity of the particle at any point is equal to its magnitude, which we call speed. And since velocity is always tangent to the path, it is always in the direction of which unit vector? ET. And I don't want to get into details of that, but if you take time derivative from this to find the acceleration of the particle, you can show that the acceleration of the particle at any point, here you have two vectors, you have two entities, v and et. V is the magnitude of speed, which can change, and et is a unit vector. Its magnitude does not change, but when object moves from one point to another, of course, et and en do change, correct? So for example, if I come here now, of course, now my ET is something like this, or let me move to another point that is more obvious. So here, then ET is going to be something like this, and then EN is going to be like that. Or if I come here, Now my ET is going to be like this, and EN is completely reversed. Okay, so clearly these unit vectors ET and EN do rotate. Okay, therefore, both of these entities have time derivatives, and so we use the product rule. It is going to be dv over dt times ET plus v times the derivative of ET with respect to time. And again, this derivative exists because ET does change the orientation. And then if you want, through simple geometry, you can show that the time derivative of this ET vector, actually the direction of it will be in the EN direction. So it is going to be EN in the EN direction, and the magnitude of it is going to be V over rho, where V is the current speed and rho is the current or the local radius of curvature. Therefore, your acceleration becomes this term, dv over dt in the ET direction. And here you have one V, another V, so it's going to be V squared divided by rho in the EN direction. Okay, so your acceleration has two terms in general, and the first term we call it tangential acceleration, AT, and V squared over rho we call it what? Normal acceleration, okay? Or sometimes we also call it centripetal acceleration. So again here, ET and EN, these are the unit vectors that you have. This is called the tangential unit vector, and this is called the normal unit vector. These are two of the three unit vectors of this new frame NT. The third one I'll show you is perpendicular to both. We call it binormal, and we talk about it, but clearly you see you can describe your velocity and acceleration well by ET and EN and by single terms. It's quite simpler than Cartesian, and we can talk about applications of this, but for now, I wanted to show you here that this rho, this radius of curvature that we talked about a lot, does appear in the calculation of what? Normal or centripetal acceleration in the NT coordinate. So if you want to know at any point how much is AN, you have to know rho at that point, and that's where you use this formula. Okay, so that's where you use it. Now, since I want to talk about a little bit about NTB coordinate here, so I'm going to show you a few things. So one is, where does this come from? The other one is, where is the binormal axis? I'll show you that as well. And then I might show you why this new coordinate frame can make life easy if you use this instead of, let's say, Cartesian coordinates. So as I said, there is a third unit vector. We call it EB, and we call this guy binormal unit vector. And this binormal unit vector can be at any point evaluated by ET cross EN. It's the cross product of ET and EN, binormal unit vector, and it's out of the plane. So for example, in here, if I want EB, the binormal, it is out of the plane. So here, if I want it, it is going to be what? Out of the plane. So this is going to be your EB, out of the plane. But in general, again, this is when you have a 3D problem and you have an arbitrary curve in 3D, So when this particle moves along this path at any point, you have the tangent direction. If this is a planar curve, then you can define En. And then EB is going to be perpendicular to both of them. Okay, so we call it binormal direction. That's one thing I wanted you to know. The other thing is, where does this formula come from? V over rho over En. I'll show you that also very fast, because I always urge my students in my classes to not accept anything from me unless I show them. And I know in this channel, in many of the videos, I have not provided proofs for many of the stuff that I wrote for you, including the row that I just used. But this one may be a good idea to take a look at that. So what I have here is I'm moving along this path. So some arbitrary path. And then at a specific point, I'm looking at the local tangent circle, something like this. And what I want is, here I'm moving from this point to another point that is infinitesimally close to it. So basically, something like that. This distance that I'm traveling between the 2 points, I would call it ds. And if the 2 points are closed, I can consider that the radius of curvature between them is not changing. So I can call both of them rho. This angle between them, I can call d theta. And what I'm after is the change in the ET vector. So if this is the first ET and this is the second ET, I want to look at the rate of change of this ET versus time. Okay, so let me develop that for you. So d of ET with respect to dt is what? The limit of delta ET over delta t, correct, when delta t goes to 0. And what I want to focus on right now is this numerator, delta ET, which is basically, in this case, it's like ET number 2 minus ET number 1. I want to look at this difference, look at the magnitude of this delta ET and the direction of it, and try to replace it back into this formula. So here, first of all, let's look at the magnitude of it. How much is the magnitude? Well, here let me make sure this second ET also in magnitude is close to the first one. So like this much, right? And clearly the angle between these two ETs, since they are both perpendicular to their corresponding rows, right? So you know the second one is perpendicular to that, the first one is perpendicular to this. Clearly this angle between them, it is d theta as well. And when I say ET2 minus ET1, it's the vector that connects the end of positive to the end of negative. So basically what I need is to go in this direction, this guy. This guy here in green is delta ET. And if you look here, this delta ET is the third size of a triangle that you can see here, with the two sides being equal and with the magnitude of each one being 1 because they are ETs and they are unit vectors. So the magnitude of this delta ET is actually what? It is equal to magnitude of one of them, correct? Right? It's a triangle like this. Each side is 1. This angle is d theta. And what you want is this side. And clearly, if you want, you can see that it is going to be 2 times 1 sine of d theta over 2. Correct? Each one of these is 1 times sine of half d theta, and then you add them together. And when d theta is a very small angle, sine of d theta and d theta are the same thing. Correct? They will converge to the same number. So if I, instead of sine d theta over 2, I use d theta over 2, in the limit they are equal, then that 2 and this 2 would go away, and you will get what? You will get 1 times d theta. That's the magnitude of this guy. So magnitude of it, magnitude of this dE theta, ET, sorry, the magnitude of it will converge to what? 1 times d theta. Also, if you look at this other triangle that you have, here you have rho, rho, and d theta. And here you have ds. This ds, clearly based on definition of d theta in radians, is rho d theta. So from here, clearly d theta is ds over rho. And if you plug it down here, that is also going to be the magnitude of det, ds over rho. And so if I go back here, and in this definition of det, I replace it with ds over rho, then what would you get in terms of magnitude of it? Magnitude of it will be what? Let me write the magnitude down here. So the magnitude of it is going to be ds over rho over dt. And you can bring rho out. It's going to be 1 over rho ds over dt. And the definition of ds over dt is, of course, v, the speed. So there's going to be v over rho. So far I showed you that the magnitude of this vector is actually v over rho, what I claimed here, that the magnitude of it is v over rho. You can see that why. And then what about the direction of it? Is that in the en direction? And the answer is yes. If you look at here, the direction of this small delta et is almost the same as what? The direction of this en. Use a smaller marker here. It is clearly very similar to this direction, which is en. Right? If you look at the green vector and the black vector. And the smaller this angle becomes, you can easily show that these two vectors are going to be parallel. So that's why the direction of it is what? En. Okay, so now hopefully you accept from me that the acceleration of the particle is v dot or dv over dt. We call it acceleration tangential. In the t direction, this is because you're changing the speed. And this other one, which is toward the center of curvature, we call it normal, or also we call it centripetal acceleration, and that is because you are changing the direction of motion. So if you move on a straight line, for a straight line, this rho is how much? Yes, it is infinite. You can show that for a straight line, rho is infinite because this double prime is going to be 0, so it's a number divided by 0 goes to infinity. And v whatever it is, if you divide it by infinite, this whole term gonna go to 0. So as long as you are moving on a straight line, the only term you have for acceleration is because you are changing the speed, and that's what we have in rectilinear motion. But when you are changing the direction of motion, there is a term for acceleration. We call it normal or centripetal, and that is inversely proportional to the radius. In other words, the sharper you turn, which means a smaller rho, the bigger acceleration or the bigger force you need. And probably you experience that, right? If you go around the traffic circle, that is a small traffic circle, you need a lot of force to keep you on track. You need to turn your steering wheel a lot. While if you are going along a traffic circle that is rather big and it has a big row, you do not feel so much of force or acceleration. So you clearly see the use of this row, how to calculate it, and where it is used for this NT coordinate. Two more things I want to tell you to have a complete discussion. So far I have told you how to, in this NT coordinate, how to define velocity and acceleration based on ET, and the speed and derivatives of speed and the radius of curvature. What about the position? Because kinematics means position, velocity, and acceleration. What about the position? How would you describe position in this NT coordinates? Because in xy, of course, at each point the position is xi plus yj plus zk. What about here? So here, if I'm here, what's the position? The position is defined as the arc, the length of the path traveled along the path. So you sit somewhere as origin, let's say here, and if you move from origin to this point, then the position is defined as I have traveled along the path for the distance of L, and L is the length of this arc. So L, the length of the path traveled, is going to be used to define position, okay? And how would you calculate L if I have a specific function like this is y f of x, and you are moving from points with coordinates of x naught and y naught to another point where x is just arbitrary x. You know, based on your calculus, this is the integral from x naught to x of square root of 1 plus dy over dx, the whole thing squared under square root, and then integral of it dx. Okay, so this is how you describe position. The traveled distance, basically, that's what it is, correct? The traveled distance. That's what you use to define position in NT coordinates. And clearly, again, as you can see, this coordinate frame is good when you know the type of path you're traveling along, so you know the criterion for it, and you know how fast at any point you are moving along it. This makes life a lot easier than to use XY coordinate. For example, if I give you this problem where I say somebody is moving on a road uphill where the equation of the road is a mild parabola like this. Okay? You're driving along this road and the speed of your car at this point is, let's say, 50 meters per second, and it is constant. So you are trying to keep your speed of the car constant by applying proper amount of acceleration from the accelerator pedal, right? And I say if you are right now at location x equal, let's say 100 meters, what is the magnitude of acceleration of the car at this point? Right? If I tell you this, it's not really hard to do it in nt coordinate, because all you need to do is to say magnitude of acceleration in nt coordinate. Since it has two components, it has a t component and it has a n component, so it comes from the square root formula. So it is going to be the square root of basically dv over dt squared, and then plus v squared over rho, the whole thing squared. And since v is constant, it means dv over dt is 0. So all you will have, this square root and power 2 would cancel. It's going to be v squared over rho. And v at the moment is given is 50. So all you need is to calculate rho for this parabola at that point. And we have already done it. It's not a big deal, correct? You just take the first and second derivative of this, plug in the value of 100 in the formula for rho that I showed you here, and when you get rho and you have v, then you're done. That's the magnitude of acceleration, which also gives you the magnitude of force that you need on the car at that point. Now, if I ask you to resolve this problem, but this time use x, y, z, Cartesian coordinate, it's not going to be that easy. Because if you want to use, instead of ntb coordinate, if you want to use xyz coordinate, now the magnitude of acceleration is going to be the square root of the acceleration terms, which are x double dot term, correct, plus y double dot term, plus z double dot term. Now in this case there is no z, so it's just x double dot and y, or ax and ay. Right? Now, where do you get these? I don't have them, but I have the equation for what? For the path. So I have to take time derivative from this twice. The first one gives me y dot to be equal to 0.002 x times x dot. And then I need to take another time derivative, which will give me y double dot to be equal to 0.002. Here both terms have time derivative, so you will get x dot squared plus x double dot. And now in order to calculate y double dot at any point, not only you need x added, you need also x dot added and x double dot added. And guess what? You don't have any of those. So what would you do now? Right? You see? You have to use this information that v is equal to 50, and v, the magnitude of speed in this coordinate, is x dot squared plus y dot squared, the square root of that. This guy is how much? This guy is 50. Right? Now, if you look at this equation, if you plug in x in it, it gives you a relation between x dot and y dot. This equation also gives you a relation between x dot and y dot. So from these two equations, when I plug in x of 100, I have two unknowns, x dot and y dot. And they are, especially this one is nonlinear, but you can solve it 2 by 2. It's not that hard. So first, from these two equations, you have to go to these two equations by plugging x of 100, and then find what? Find x dot and find y dot. So you can use your x dot, for example, here, because x is known, and still x double dot is not known. So now you have to take a time derivative out of this, and time derivative of, if you want, you can first raise them to power 2, so you don't have to take time derivative of the square root. So you only take time derivative of x dot squared and y dot squared, and that is going to be 2x dot x double dot, and then plus 2y dot y double dot. Time derivative of constant is 0. And now in this equation, you know x dot, you know y dot, you don't know the double dots. So now you combine these two equations, this one and this one, and now these equations will give you what? These equations will give you x double dot and y double dot. Now you can finally use here to find acceleration. So you have to take several time derivatives, use the chain rule, then solve a 2 by 2 here, solve another 2 by 2 here, and finally plug it into this equation to give you magnitude acceleration, while here all you need to do is to find rho at the point and plug it into the simple formula and get your acceleration. So NT coordinate is, if used properly, can make life significantly easier on you. And I assume I told you most of the stuff that you need to know about NT coordinate. And I want to use this formula one time also, since I mentioned it. I want to use it one time and show you how this works. And then I guess I'm good about radius of curvature and the NT coordinate. So the last thing I want to do is to use that formula on something that you know and make life a little bit more convenient to you by understanding how to use this. And again, here I'm going to go with the circle example. So here I have a circle, and this circle, I'm going to measure its circumference, right? So circumference is going to be twice the length of the path from, or I can say, 4 times the length of the path from this point to this point, right? So I can say this is x naught and this is x. And if I calculate the length of this arc and multiply it by 4, that is going to be the circumference. So what is this guy? This is the integral from x naught, which is 0, to x. Now here, let's say the radius is whatever you want, r units, or 1. Let's make it 1 to make it easier. So from 0 to 1 of what? Square root of 1 plus y prime squared dx. Now the equation for this path is clearly x squared plus y squared equal 1 squared. And therefore, y is going to be square roots of 1 minus x squared. Again, positive, negative it has, but since here is y positive, I use the positive of that. And here I need to take a derivative. Y prime is going to be negative x over square root 1 minus x squared, which you know from your calc. So this is going to be, it is going to be equal to integral from 0 to 1 of square root of, and here it's going to be 1 plus that whole thing squared. And if I continue, here this term under the square root is going to be x squared over 1 minus x squared. And if you take common denominator, 1 minus x squared plus x squared will be summed to 1. So this is going to be square root of 1 over 1 minus x squared dx. And so 1 can come out. And if you know this, this is the arc sine function. So there's going to be sine inverse of x calculated at 1 and 0, which is going to be pi over 2 minus 0, which is pi over 2. And this pi over 2 is what? 1/4 of the circumference. So the total circumference is going to be 4 times L, and 4 times pi over 2 is what? 2 pi. And you know that's right, because the circumference of a circle is 2 pi times r, and r here is 1. So you can write it like this. And that's right. So you clearly see that this arc length formula works just fine. So hopefully now I have given you enough of info. Thank you.